This video is going to be about isotopes and radioactivity. Isotopes are the forms of an element with the same number of protons but a different number of neutrons. This is possible because only the number of protons, or the Z number, determine the element and its chemical properties. For example, if I were to take hydrogen 1,1, and I could also make hydrogen with an atomic mass of 2, and I could also make hydrogen with an atomic mass of 3. All of my hydrogen isotopes I've just drawn out have the same number of protons, or atomic number, 1, but they all have different mass numbers, 1, 2, and 3. So because all 3 have an atomic number of 1, they're all isotopes of hydrogen. And each hydrogen's kind of fun because it has unique names for its isotopes. There's protium, deuterium, and tritium. Most isotopes are unstable, and this is why they emit radioactivity, randomly and spontaneously, to carry the extra energy away from the nucleus, so they can become more stable. This diagram shows different numbers of neutrons versus atomic numbers, and you'll notice there's a black band that runs down the middle, where it says these are stable nuclei. This is the band of stability. So there's kind of a magic number between neutrons to protons that make you, or neutrons to atomic number, to give you a stable nucleus. If you're above the band of stability, usually you'll do beta negative decay to become more like the atom in the band of nucleus in the band of stability. If you're below, you'll do beta positive decay to become more like a nucleus in the band of stability. If you're too large, normally you'll emit bigger particles through alpha decay. And so we'll go through what each of those 3 types of decay are right now. So alpha decay is what you do when your nucleus is just too big and you need to get rid of some nucleons to become more stable. Alpha decay decreases the nucleon number of your starting nucleus by 4, so you'll lose 4 nucleons total. So for example, if I were to take radium-226 and I were to emit an alpha particle, which has 4 nucleons, 2 of which are protons, 4 and 2. This is my alpha particle. I would reduce the nucleon number of radium by 4, and I would reduce the atomic number by 2, which would mean I have a different element now because I've changed my atomic number. Now I have radon. Okay, that's our example of alpha decay. You guys should know the general format for alpha, beta, positron, and gamma decay, so that way you can use it on different kinds of elements. So we'll start with our nucleon notation, AXZ. We'll emit an alpha particle from our general AXZ nucleon. And so if this happened, I would reduce A by 4, so A minus 4. I would reduce Z, the atomic number, by 2. And remember, when you change the atomic number, you change what element you are. And so I'm no longer element X, I'm now element Y. That's alpha decay. So now let's look at negative beta decay, or beta minus decay. So beta minus decay occurs when your nucleus doesn't have enough protons to be stable. And so you convert a neutron to a proton, and an electron is ejected from your nucleus. In this type of decay, the atomic number increases by 1, but the atomic mass will stay the same because I'm exchanging a neutron for a proton. So in our example, iodine 131 is going to do beta negative decay. And so it'll keep the same atomic mass because I'm changing a neutron for a proton, but I'll gain an atomic number. And when I add 1 to my atomic number, I become xenon. So then I emit my beta particle. A beta particle is negative. It's a high energy electron, so it's negative. And a new particle, an anti-neutrino. I know it's an anti-neutrino because it's got a bar above it. That's my beta particle and my anti-neutrino. So the general structure for beta negative decay, my atomic mass stays the same. I add 1 to Z, and when I change the atomic number, I change elements, so I need a different symbol. And I emit my beta particle and my anti-neutrino. Okay, remember you guys need to know these general formats. They're not in the data book. Now let's look at positron decay, or beta plus decay. In positron decay, the nucleus emits a positron and a neutrino. A positron is like a positively charged electron. And this happens when a proton is converted to a neutron. So this is done in nuclei that need more neutrons to become stable. So for example, in neon 19, I'd switch a proton to a neutron, so my atomic mass stays the same. So I'm losing one and gaining one, but my atomic number decreases by 1. And because I decreased my atomic number by 1, I become fluorine. A positron has a positive charge, and I emit a neutrino. This is the positron, and this is the neutrino. Remember, you can tell the difference between a neutrino and an antineutrino, because the antineutrino has a bar above it, and the neutrino does not. So if we look at the general structure for positron decay, keep the same atomic mass, and we decrease our atomic number by 1. So because we decreased our atomic number, we become a different element, and we have our positron and our neutrino. All right, the last type of radiation we're going to talk about is gamma ray emission. So gamma rays are high energy photons which are emitted from the nucleus. Remember, gamma rays are at the far end of the electromagnetic spectrum. And remember, we released photons when we dropped energy levels for the electrons before. So let's look at kind of a radium example of how gamma rays work. So if I have radium-226, there's 2 ways for it to become more stable, and both end with it becoming radon-222. The first way is for it to get rid of all the energy in one go by giving it to an alpha particle. It has lots of energy, 4.76 or 4.78 mega electron volts. So it gave all the energy that it needed to become stable away to the alpha particle. The other way is to give some of the energy away to an alpha particle, but this leaves, so instead of 4.78 mega electron volts, this alpha particle would only have 4.59 mega electron volts. And that leaves our radon in an excited state. And so this nucleus has to drop back down to the ground state. And when it drops back down, that energy has to go somewhere. And so it emits an alpha particle. And so the alpha particle is equal to the difference in energies of 4.78 mega electron volts and 4.59 mega electron volts. And so that's where the gamma particle comes from. The other thing this shows is that alpha in gamma particle emission is quantized. So it either has to be 4.78, 4.59, and whatever the difference between those numbers is. And this shows that the nucleus has quantized energy levels, just like the electron orbitals had electron energy levels, or that were quantized. All right, that's the end.